In the last lesson, we learned about arcs and chords and how to find the measures of those things. And today we're going to talk about how to find angle measures and segment lengths as they are associated with circles. So let's start with the definition of a line that intersects a circle at 2 points. Here's what this looks like. Circle, line, intersects at 2 points. We'll call that AB. That line is called a secant. Line that intersects a circle at 2 points. And as you can see here, AB is also a chord, right? Segment AB is a chord. So sometimes you'll hear a chord referred to as a secant segment, but the line itself is known as a secant. Line that intersects a circle at 2 points. Okay, we got a couple of theorems here. The first one says the measure of an angle formed by two lines that intersect inside a circle is half the sum of the measures of the intercepted arcs. So for instance, if we take this picture here, and let's say we let y be 80 degrees, and let's let x be, I don't know, 84. I'm going to make it even so it doesn't come out to be a fraction. So what we know is, because of that theorem, that the measure of angle 1 is 1/2 the sum of those arc measures, 84 plus 80. So that's going to be 1/2 of 164. So the measure of angle 1 would be 82 degrees there. And of course that would also be the measure of this angle here. Why? Because they're vertical angles, and vertical angles are congruent. Okay, what does the next theorem say? The measure of an angle formed by two lines that intersect outside a circle. So the first theorem up there was for lines that intersect inside a circle. This one for lines that intersect outside a circle. And these lines don't necessarily have to be secant lines either. They can be tangents or secants. As you can see, this line here is a tangent. Both of these are tangents. But this theorem applies to both tangents and secants. So what I know is that the measure of that angle formed by the intersection of those lines is 1/2 the difference. 1/2 the difference of those arc measures. So let's just put an example up here. Let's say x here is, I don't know, 120. And let's say this arc here would measure, I'll just say 20. Just making things up here. So what I've learned in this theorem is that the measure of angle 1 is 1/2 the difference. And of course I'm going to take the larger one minus the smaller one. So that would be 1/2 of 100. So the measure of that angle 1 there would be 50 degrees. And it doesn't really look like it's that large, but as you know, I made those numbers up just for demonstration purposes. Okay, here's an example for us. What is the value of each variable? Well, we're gonna have to use the second theorem that we just learned, right? So I know the measure of the angle is 1/2 the difference of the measures of the arcs, and W is the larger arc. So W minus 110. So that's going to be, oh, but we know the measure of the angle. So let me substitute that in. 70 is 1/2 of W minus 110. So multiply both sides by 2. Solve for W, and we get W is 250 degrees. And the degrees is already there, so I don't have to add it here. And look, guys, if you look at this closely, I can see this arc here measures 110. And the other arc is the rest of the circle. So, of course, it had to be 360 minus 110, which is 250. Check your answers to make sure they make sense. Okay, how about this one? This, again, is the second theorem that says if two lines intersect outside a circle, then the measure of the angle formed by those two lines is half the difference of the measures of those arcs. So here we go. So I know that y is going to be half the difference of the measures of the arcs. So 110 minus 30. All right, so I get 1/2 of 80, which means y there is going to be 40. 40 degrees is the measure of that angle. Okay, this one, the two lines are intersecting inside the circle. So pause here and do this problem and come back and check it. Okay, did you get 40? Hope so. set up my equation there that tells me the measure of the angle is 1/2 the sum of the measures of the arcs, substituted in all the values that I know, got 40 there for x. So if you didn't get that, see if you can figure out why. If not, let me know in class and we'll go over it. Okay, some more theorems. Now we're moving on from arc measures to segment lengths. All right, angle measures. Now we're moving on to segment lengths. So we got a theorem here, and it might not make much sense when we read the words, but I promise we'll make it make sense. The theorem says, for a given point and circle, the product of the lengths of the two segments from the point to the circle is constant along any line through the point and circle. I agree. Wow. If I had to figure that out on my own, I probably couldn't do that. So here's all that is saying. Okay, so for the first case, I got 3 cases here. First case is, I've got 2 segments, 2 chords that intersect inside a circle right there. So the first part tells me that if I just do the 2 parts of each chord, the product of the 2 parts of one chord equals the product of the 2 parts of the other chord. So if you see A is one part of this chord, B is the other part. So if I take the product of those two, take the product of the parts of the other chord, those 2 things will be equal. Okay, part times part equals part times part. Okay, now, in the next 2 cases, we have the lines or the segments intersecting outside the circle. So what we know is, and you can look at this theorem here, this equation, but the way I like to remember this, these two cases right here, just think of this. Ow, ow, right? Pretend like it hurts. Maybe it actually hurts. Maybe you don't have to pretend. But what this means is that the outside of the segment times the whole segment equals the outside of the other segment times the whole segment. Outside times the whole equals outside times the whole. Ow, ow. Okay, so let's look at this. So if I take the blue segment here, the outside of it is W, and the whole length, the entire length of that segment, is W plus X. And the other segment, our red one, the outside of it is Y, and the whole segment is Y plus Z. So it's kind of reversed here. Outside times the whole equals outside times the whole. I don't know, I just thought you could remember it better using ow, ow instead of whoa, whoa. But whatever you like. Okay, and the same thing applies here, except it looks different. So let's look at our first segment here. This tangent to the circle, the outside of it is T, and the whole thing is also T. So that's where the T squared comes from. And then the outside of the red segment is Y, and the whole segment is Y plus Z. So ow, ow still applies. All right, let's do some practice. Let's see how many we got here. How many do I want to do, and how many do I want to let you do? Okay, we'll just start, and then we'll figure it out as we go. Chords JN and KM intersect inside the circle. Okay, so this is where the first case of this theorem applies. And so we're going to do part times part equals part times part. That's what you do if they intersect inside the circle. So let's take this one first. 10 times X, those are the 2 parts of that chord. 2 parts of this chord are 8 and 5. So I end up with 10x equals 40. So x equals 4. Not too bad, huh? Okay, how about this one? They're intersecting outside the circle. So this is where I have to use outside whole equals outside times the whole. Ow, ow. So let's look at AC first. The outside is 12. The whole thing is x plus 12. And now if I look at AE, the outside is 15, and the whole thing is 24, right? 9 plus 15. Okay, so now watch this. Before I distribute this 12, I'm going to step back here and take a minute and say, wouldn't it be easier if I divide both sides by 12 instead of distributing that 12? Because look what's going to happen. If I do that, Divide by 12, divide by 12. Oh, that's nice. 12 goes into that 1, 12 goes into that 2. Those cancel each other out. And then I just have x plus 12 equals 30. And then I can easily get x equals 18. And I promise you, you'll get the same answer if you distribute this 12 up here. If you go ahead and say 12x plus 144 equals 15 times 24. I don't even know what that is. Let's see. 15 times 24, 0, 2, 6, 0, 3, 360. Wow. See, I don't want to deal with those big numbers. I don't want to have to do that. So I'm going to save my resources and do things in the easiest way possible. All right, what's our next example? Oh, these are the practice problems. And you know what? I'm going to do these, I'll do all these with you because the answers don't really come out all that nicely, unfortunately. So let's see. Let's start with this circle here first. Let's start with this circle. Take it by itself. And I've got an ow-ow situation, right? 10 squared equals 6 times the whole thing, which is x plus 6. So I got 100 equals 6x plus 36. So 64 equals 6x, which tells me that x is 64/6, which is 32/3. Told you, didn't come out all that nice. Okay, now let's do the other circle to figure out what y is. I know that y squared equals, so that's outside times the whole, equals the outside times the whole thing, which is 32/3 plus 6, right? Because we got to plug in 32/3 for x. So y squared is, let's see, 3 will go into that 2. So that'll be 64 plus 36, which is 100. So therefore y equals 10. I thought it was going to be 10 because it looks the same, but I really can't just decide that's the same just because it looks the same, right? Okay, what do we got here? We got intersections inside the circle. So I think if I could figure out what this piece measures, oh, but wait, I can, right? Because look here, guys. This arc right here is bisected. You see how it's marked? It's bisected. That means this chord here is bisected. So that would be congruent to that, which would make that 5. And then that means that this diameter is perpendicular to that chord, right? So we learned all about that last time. So what we got to do here, we got to do part times part using these two chords, the blue one and the green one, and we don't know what x or y is. How can we find x? Oh, we got a right triangle. So let's say x squared plus 5 squared equals 12 squared, just straight up using the Pythagorean theorem. So x squared is 144 minus 25. And let's see, 144, 25, 9. 13 minus 2 is 11. So therefore, x is going to be the square root of 119. Not looking good. Not looking good, guys. This is why I wanted to do this one with you, because as far as I know, I can't simplify the square root of 119. I think it's prime. Okay, so if that's x, then we're going to do, so here we go, 119. So we're going to do part times part equals part times part. Okay, well the blue chord is 5 times 5. I know that. And now I know that equals x times y, right? The diameter. So we got 25 equals, and now I know what x is. It's the square root of 119 times y. So that tells me, I'm going to come up here, y is 25 times the square root of 119. And as you know, we can't leave that radical in the denominator, so when I rationalize that thing, I'm going to end up with y being 25 times the square root of 119 over 119. That's dreadful. If you had that on a test, I'd probably just say, go ahead and use your calculator and round it off to some decimal, because that doesn't really give me a good idea in my head of how long y really is, or x either for that matter. But anyway, that's just application of the theorem, and that's what we really wanted to practice. Okay, now here's a problem that we have had. We had two like this, I think, in the very first lesson, or at least we've had a couple, I think, throughout these lessons. So I want you to pause right here, look back at your notes, and work this problem and come back and check it. Okay, did you get that the radius is 55 halves? Or if you wanted to make that a mixed number, let's see, 22.5 feet. Well, I want you, if you did, great. If you didn't, I want you to see if you can figure out why. But I also want you to see if you did get this answer, if you did it like I did here. What I did is I applied the new theorem that we learned, right? And so I got outside times the whole, so 24 squared here, equals the outside, which is 9 down here, times the whole, so that's 9 plus, and where does this 2r come from? Where does this 2r come from? If you didn't do it this way, I want you to think about that and see if you can figure out why I've got that 2r there. And I'm going to leave you with that. I don't want to spoil the fun and tell you, but be sure that you look at this and that you are able to at least try to tell me where that 2r came from in my equation there. All right? That's it for angle measures and segment lengths. We'll see you next time.